Hi, my name is Riwan Kuna. I'm a student engineer studying at ENSTA Bretagne, a graduate and postgraduate engineering school and a research institute located in Brest, France. What I'm going to talk about today is a project named SpecEdit. SpecEdit being a contraction of specification and editor. My presentation is going to hinge around the following main topics: the idea behind SpecEdit, the creation of a language model, plain text support, user experience customization, what SpecEdit concretely brings about, what has been achieved so far, and what is yet to be done. SpecEdit is an integrated development environment, or IDE, dedicated to TLA+, which stands for Temporal Logic of Action, a high-level specification language created by Leslie Lamport for the description of reactive, distributed, and especially asynchronous systems. Amongst its industrial uses, let us quote its use in production for capturing the design requirements of today's most influential cloud infrastructures, namely S3 from Amazon, Azure from Microsoft, and Elasticsearch. You may wonder why create an IDE for TLA+, since there is already an existing one named TLA+ Toolbox, and which provides a state-of-the-art formal specification ecosystem. Well, at the syntactic level, TLA+ suffers from the duality of its syntax. The syntax of TLA+ finds its roots in mathematical notation and features more than 80 non-ASCII mathematical symbols. Concise but expressive, the mathematical syntax is, however, historically not well supported by text editors and IDEs. For TLA+, this led to the fallback of using mnemonic ASCII words. Consider, for instance, the subset operator, which is represented by the subset EC mnemonic in the TLA+ ASCII syntax. Although listed in the language documentation, these mnemonics considerably steepen the learning curve due to the need to look up the notation corresponding to the wanted symbol. Moreover, once the mnemonic is inserted in an editor, the specification designer either has to become accustomed with thinking in terms of ASCII notation or continuously generate and compile a LaTeX-based PDF representation of the specification as offered in TLA+ Toolbox. TLA+ Toolbox lacks not only the much needed mathematical symbols, but also many features proposed by the current IDEs. Is it then possible to hide TLA+ syntax duality in a viable bilingual IDE to reduce the mental efforts of system engineers? Well, you may suggest to simply consider only keeping the ASCII syntax. However, to paraphrase Leslie Lamport, when it comes to the pre-printed version versus the ASCII version of TLA+, one of the good things about TLA+ is that if you don't understand what a TLA+ construct means, you can look it up in a math book. Math books don't write math in ASCII, they use 10 mathematical symbols. My colleagues and I thus wanted an IDE that would expose only the mathematical syntax to the user, translating it to the ASCII version, ensuring compatibility with existing tools. Let us focus first on the mathematical syntax exposure. At first glance, this does not seem so trivial because the input device we use, the keyboard, does not allow for the direct input of special characters. Furthermore, the use of the Unicode ID or of complex key combinations needed for writing the corresponding Unicode characters is clearly no better solution. This is where JetBrains MetaProgramming System MPS steps in, which offers a language design workbench based on projectional editing. Why this choice? First, because MPS helps producing editors that allow the mixing of graphical, textual, and mathematical notations, and this is particularly adapted to the syntax problem of TLA+ we wanted to address. This is made possible thanks to projectional editing that works directly on abstract syntax trees, ASTs, trees representing syntactic structures and that correspond to the underlying language model. Furthermore, not only does MPS provide a solution for visualizing the mathematical syntax, but it relies upon intentional programming and provides adequate input mechanism via user interface actions. This being said, exposing the mathematical syntax via a projectional editor does not mean that there is also an underlying plaintext ASCII version of the lines of code that could be then used to ensure the compatibility of SpecEdit with existing TLA Plus tools. Indeed, the projectional editor persists the abstract representation in a storage representation, but it is entirely separated from any of the editable representation that it projects. Before going further into the details, let's take a step back and oversee the global architecture of SpecEdit, which deals with this concern for backward compatibility. In the figure, the core components of SpecEdit are highlighted by green, representing meta models, and blue boxes representing the tools. The projectional editor displays the TLA Plus model that is instantiated based on user input. As usual, the model confirms to the meta model. The backend is composed of a paste handler, a writer, and a reader. SpecEdit supports copy-paste both internally by exchanging AST nodes through the writer clipboard reader path, and externally by processing plain text coming from the system clipboard via the paste handler. This means that users can copy plain text TLA plus lines of code and paste them directly in the projectional editor. The writer represents the serialization modules, which, based on the persistence model, output different file-based representation of the model. The reader represents the file input modules, which can instantiate the TLA plus model according to the persistence model and after passing the files according to the respective grammar rules. SpecEdit backend supports an internal XML based with serialization format, but also TLA plus ASCII files. This means that SpecEdit allows users to directly load or save plaintext TLA plus files. Let us start by focusing on the projectional editor and the underlying models. The first step in creating a projectional editor for TLA plus was to define a language meta model. What can be found in the literature is the model given by the creator of TLA Plus to define its language in the form of a grammar. A grammar, in computer science, describes how from a language's alphabet to form strings that are valid according to the language's syntax. To define the underlying language meta model in MPS, the TLA Plus grammar was converted into a set of MPS concepts which represent the abstract syntax, types and hierarchy of AST nodes, and reference children nodes, parent nodes, properties of primary data types, etc., etc. This meant identifying classes out of the grammar for the object-oriented infrastructure provided by MPS and relations between those classes in order to fill in parent and children nodes of the different corresponding concepts. The extraction of the language concepts from the concrete syntax resulted in a meta model with 110 interconnected concepts. On the slide, you can see the grammar rule corresponding to a TLA plus module and the corresponding equivalent in MPS. Module name designates a mandatory string that must be entered by the user, set of module names optional strings, and set of units a set of expressions and statements that may constitute the TLA plus module. Next step, after defining the model, was to define its rendering in the IDE, that is, the definition of a concrete syntax. Each concept was thus associated with a specific MPS concept editor. From the model view controller design pattern perspective, these concept editors play the role of views and controllers for the associated language concepts. Since Unicode characters are supported by MPS, they were used to customize the editors and thus to obtain a rendering that integrates the mathematical notation, like for instance the arrow in the figure at the top. To also allow users to insert mathematical symbols, MPS enums were used. Enumerations in MPS allow to define properties with values from predefined sets. The possible values are shown in a context menu if the given values can be inserted at the current cursor position, according to the meta model. The figure on the bottom shows the mapping between the TLA plus grammar rule prefix up and the corresponding MPS enum, as well as the rendering in the completion menu when prompted to users. Since we are here dealing with projectional editing, manipulating plain text is not as easy as it seems. This means dealing with model transformation in order to ensure the backward compatibility of SpecEdit. More precisely, we had to deal with model-to-text and text-to-model transformation. Let us start with the paste handler. As its name suggests, a paste handler is in charge of managing paste events. When a user tries to paste an element into the IDE, a background routine is in charge of retrieving the clipboard content to insert it in the editor. The only way to do so is to parse the text from the clipboard in order to interpret it and instantiate the corresponding elements in a new model. SpecEdit uses the Antler parser generator framework and the TLA plus grammar definition to process plain text. Antler builds a parse tree and generates a skeleton visitor class containing methods for traversing parse trees. In the case of SpecEdit, the corresponding visitor class is subclassed and each visit method overridden to instantiate MPS concepts. The text retrieved from the clipboard, which is tokenized, parsed, visited, and mapped with MPS concepts, allows the instantiation of an AST. The compiled code and voice dependencies were integrated in a dedicated plugin, inserting a new entry in the context menu for pasting plain text. Moving on to the custom persistence model, MPS normally saves models in its own XML-based format. However, with a custom persistence model, this format can be changed. The idea we had was to create a custom persistence model allowing to remove any formatting specific to the IDE in order to save the TLA plus source code files directly in plain text, thus gaining interoperability of the files saved on the disk. This implied modifying the file loading and saving strategy of the IDE. Apart from the import source, which is a file and not the clipboard, the processing principle for loading ASCII TLA plus files is exactly the same as for the paste handler. The writing procedure is, however, delegated to text generators implemented via MPS TextGens. Note that we created an explicit plugin descriptor for MPS to understand that this plugin provides a model factory. Now that the model, view, and generation definition processes have been described, the next step is to see how user experience was optimized in SpecEdit. I will focus on the controller aspect of concept editors in MPS. In a projectional editor, users do not write code, but they instantiate model elements via numerous specialized editors. MPS gives the possibility to use the completion menu to select a new node to be instantiated. This process is slow and very frustrating when not combined with free editing. This is why we decided to overcome this limitation. Free editing combined with reference resolution, a functionality I won't be using in this presentation, optimizes user experience of SpecEdit. To allow free editing, programmers have to make fields editable in MPS editors. Once done, users will be able to input via keyboard, but MPS will point to syntax errors since keyboard typing won't instantiate new concepts. To solve this issue, predefined strings were mapped to the concept via MPS aliases and the MPS transformation manual language, which allows to trigger actions when given patterns are identified, and in particular, they allow to instantiate corresponding model elements. Another editing issue we faced was hiding optional model elements when they are not needed. For instance, in TLA+, a module can optionally extend other modules. On the figure, the optional block is shown as a set of cells preceded by a question mark. In the case of a standalone TLA+ module, the extends clause should be hidden. However, if it is hidden, there is no mechanism defined to allow users to make it appear and thus import modules. We accordingly managed to capture this user intention by combining the use of display conditions with side transform actions, implementing specific mechanism in the editor. In the example I was giving, a transformation menu can be invoked by a user typing extends right to the cell it has been associated with, which makes the hidden field to appear. SpecEdit in practice. Well, SpecEdit benefits extensively from the architecture provided by MPS. The resulting multi-platform standalone IDE provides basic features of an IDE like syntax highlighting, tree view, autocompletion, predictions, syntax verification, reference resolution, free editing support, etc., etc. But also mathematical notation support, freeing TLA+ users from the ASCII syntax, and plain text support, which preserves the compatibility with other tools. I mentioned Elasticsearch during the introduction of this presentation. Elasticsearch is a distributed search engine developed in Java. The Elasticsearch designers relied on TLA+ for the specification and the validation of their cluster coordination model. For illustration purposes, I've selected one definition from the specification, which is presented on this slide, with, for comparison, the same definition in SpecEdit. Compared to the ASCII specification, note the use of the standard mathematical symbols for the existential and universal quantifiers instead of \e and \a. Also the set inclusion operator instead of \in, and well, many others. Not having to deviate from mathematical writing in both writing and reading is what contributes to streamlining the engineering process and reducing the mental effort needed. So the projectional approach is not the most widespread approach in code editors nowadays. It, however, has the potential to play an important role in the future to map language definition to any syntax. Furthermore, the projectional editor, though self-sufficient, combined with a traditional parsing approach, addresses the concern of interoperability in the specific context of TLA+ by providing a bridge between SpecEdit and the existing TLA+ tools. SpecEdit provides a solution that unifies the two existing syntaxes of TLA+ and eases the work of engineers. To do so, not only was it necessary to formalize a new model of the language, but also was it crucial to work on the input nodes provided to the users. SpecEdit is not yet a full-fledged IDE. It is meant, however, at epitomizing what can be achieved through projectional technology to improve the experience of systems engineers using specification languages such as, but not limited to, TLA+. Moving on to some future research directions, we are contemplating the use of model federations to ensure the traceability of textual requirements translated into TLA+ specification via SpecEdit. We are also considering the implementation of voice projection for TLA+ specifications based on tabular and/or graphical editors. The GitHub repository of SpecEdit is available at github.com/k1c/specedit, together with a demo video which illustrates the features offered by the IDE as well as its usability. Of course, feel free to contribute to the project on GitHub. Thank you for your attention.